Hello everyone, and welcome to our webinar titled From Ancient Relics to Life on Mars, How Temperature-Controlled Experiments Aid Materials Characterization. Thank you all for being here, and thank you especially to the presenters from the University of the Basque Country in Spain who are going to talk about their work today. Just a quick note to say, if you have any questions, if you're watching this on catch-up on our YouTube, please feel free to leave those in the comments or send them to us by email, and we will get back to you about those.
So, and if you have any problems with that, you'll feel free to send me an email or any of the presenters that you can. And yeah, we'd love to answer the questions. So, without further ado, let me just start with a little brief introduction to Linkam and why this is such an exciting prospect for us to be able to work with this group. We're Linkam. We're a small family-owned company in just outside London in the UK, and our main thing is temperature control or temperature environmental control for sample characterization and analysis. So we're really interested in any type of experiment that uses that requires temperature to be carefully controlled in order to observe changes or in materials, and all sorts of materials. I think obviously we're going to focus on a few in particular, but I think all I want to start by saying is that this is something that's really important in all research areas, and we're so privileged to be able to work with researchers across different fields and see in all different types of research how they use our products to help their experiments. So I'm just going to spend about 1 or 2 minutes to give you an example of some extremes of what we work with before I hand over to the stars of the show today. So the first is a high temperature example in metal work. So this is using one of our stages to, here we go. I've sped through a second. Okay, so here's just a quick example of what you can do at high temperature. So this is a group at the Diamond Light Centre in the UK, and they use some of our high temperature stages to look at metal alloys. And one of the key things they did in this work is to have a setup that allowed them to look at the materials for very long periods. So over a 50-day period, they kept the materials at 800 degrees, and they essentially mapped the structure and the phase, mapped the hardness and crystallinity of the material as it changed, and how the different phases in the material changed over these 50 days, and saw different phases grow, which they can associate with toughness and anti-corrosion. So that was a really nice example of high temperature work. So now moving on to a very low temperature application. So this is about as low as we go with using liquid nitrogen to cool your samples down to about, or just below 195, minus 195 degrees C. So this is an example from a group in Warwick, also in the UK, who have some cancer cells which they target with organoiridium photo-excited compound, and they, as you can see here, they find the cells and target them and attack them with these photosensitive particles, and find that they're able to shrink and attack specifically the cancer cells. So this is a nice work which is really made possible by being able to vitrify the cells, which requires it to be at very low and very controlled temperature, which they do using this stage here. and that also allows them to switch their samples out between different devices. So you can go between from a microscope to any spectroscope or X-ray device, which is a really neat low temperature application. So, all right, that's the end of my introduction to tell you the scope of sort of a higher temperature or down to a lower temperature and everywhere in between. But of course, what we really want to focus on today are how this temperature control and temperature control experiments and their relevance for looking at both historical artifacts and relics, and how those same techniques are useful for looking at aerospace applications, in particular those Martian rock samples. So at this point, I'm going to hand you over to Juan Manuel Madariaga, who is the professor and chair of the rest of this session, professor of analytical chemistry at the University of the Basque Country in Leioa in the north of Spain. He's been a professor there for over 25 years. He's part of the European Network for Research in Heritage Science and coordinator of the Spanish Network for Geochemical Studies of Mars. He, of course, focuses on these archaeological and extraterrestrial materials characterization, and as you may know, he's involved in the current Mars mission and the future ExoMars missions in 2022, and he has over 300 publications in these fields. And I think we're very, very happy for him and his students to be able to join us here. So thank you once again, Manuel, and let me pass over to you.
Thank you, Robert. And thank you for giving us the opportunity to explain and describe a couple of works we have made. First, I would like to start putting in context our work in two of the field areas of research we are conducting nowadays. In the next slide, there is an explanation for our name. We are officially called it IBEA Research Group. This is coming from the Basque language. It means Research and Innovation in Analytical Chemistry, and we are qualified as a research group of excellence since 2002, after periodical evaluations of 3 years conducted by an international panel of experts under the supervision of the Basque government. Next slide, Robert. In the field of cultural heritage, we started at the beginning of this century applying Raman spectroscopy by using a Fourier transform spectrometer. And we published our first work in 21 on historical wallpapers. Can you see the image in the left, the very poor state of conservation of the wallpaper, and in the right, the final work after the restoration, following the identification of the pigments we detected using this Fourier transform Raman spectroscopy. This technique is a problem because it requires the scrapping few samples from the wallpapers, and for working in cultural heritage nowadays, this is not the first stage of the work. It is better to start with in situ measurements using portable equipment. This is what we made a couple of years later. Next slide, please. When we incorporate our first portable Raman device, 800 by Renishow, and we started performing research on mural paintings in medieval churches, and we detected nearly from the beginning, even using these portable devices, degradations, a lot of different degradation in the different sites we were studying, especially in churches in the Spanish Atlantic area. This is one of the examples. Here you have a couple of papers that have received more than 60 sites in the history of those contributions. Times evolved and new generations of portable instruments came, and we incorporate, as you can see in the next slide, a new family of portable Raman spectrometers by black and white technologies, now in the hands of Metron. And we coupled motorized stage tripod with a capability of 1 micron per electrical pulses in the 3 direction of the axis to perform in situ Raman spectroscopy. You have here a couple of examples in the field. This is in a house of Pompeii, analyzing remainings in the wall paintings, and also in the Naples National Museum of Archaeology, analyzing panels that were 150 years ago, more or less, removed from the city of Pompeii. Unfortunately, as they made that more than 1.5 centuries ago, we can appreciate the beautiness of the paintings, because most of the panels that are now surviving in the houses in Pompeii are really degraded. In the red and white areas of these panels deposited in the museum, we detected some kind of blackening processes. I'm going to talk about this a little bit later. But we also applied this technology in the next slide to other sites of the heritage. This is the Levantine rock art in shelters. This is open air shelters, and we could perform micro Raman spectroscopy with the same device, and we can detect different, even in this spectrum I am showing, 4 different compounds in only one spectrum, in one spot. And in the next slide, the same device in the top of a scaffolding, measuring the mural paintings of the medieval churches. Next one. Here and in most of the examples, we detected these kind of degradations, and not always we could analyze pretty well with the portable instruments. That's why in sometimes we take samples and we send the samples to the next instrumental devices I am going to show you in the next slide. This is the structural and chemical analyzer. This is a complex instrumental setup. In the left, you can see an scanning electron microscope with a detector of energy dispersive X-ray fluorescence, and in the right, you can see the Raman spectrometer. In the middle, there is an interface by means of what we can measure in the same spot with the 3 techniques. So we obtain a lot of information from the small amount of samples we can take from the panels of the paintings. This started in 2028, but this was also the instrument that we used to start with a new field of research. In the next slide is the analysis of the extraterrestrial materials and the impact glaciers forming in Earth by the action, the extreme pressure and heating due to a high velocity bolide that entered to the Earth atmosphere. This device has been critical for our growing in the analysis of these kind of extraterrestrial materials. Next slide. because we incorporated to this device, you can see in this example, how from all of the images we collect, the high amount of information we can extract from very, very thin sections and very, very low in size of the spots. To increase that, we incorporate by the first time a Linkam stage to the system. Next slide. And we performed this work, how the different mineral phases in the calcium sulfate can change as a function of temperature. And we could define something like 5 different phases of calcium sulfate. Gypsum, that is the 2-hydrated basanite, that is half hydrated, anhydrite type 3, anhydrite type 2, anhydrite type 1. This work has received a lot of sites in the literature and was our first approach to the use of the temperature control Linkam stage to the Raman spectrometer. Next slide. And as Robert said in the introduction, in 2015, we were included in the ExoMars Mars 2020 science teams. And to do that, we incorporated another stage, the stage that can go from minus 160 degrees till 600. Because in Mars, we have extreme low temperatures. And if we wish to analyze meteorites, we need to go a little bit higher, more than 400, in order to simulate what is happening with the entry of the meteorites in the Earth atmosphere. And this incredibly can be also applied in the field of cultural heritage. And now we are going to present a couple of examples of the work we have done in the last 2 years in both fields. We will start with Ilaria Constantini. She performed together with us, some of us in 2019, work on the problems related with the thermal transformation of lead pigments, in particular lead dioxide, the platinum. So I give you the word to Ilaria to give you details of this quite nice research piece of work.
Thank you, Juan Manuel. You can see the presentation. Okay. Good morning, everyone. I'm Ilaria Costantini. I'm a researcher of the IBEA group in the Department of Analytical Chemistry of the University of the Basque Country. My investigation concerned the study of the conservation state of cultural heritage material, in particular of mural painting and building materials, and the impact that natural and anthropogenic factors have in their conservation. In the file of cultural heritage, the use of the temperature control stage is very useful to investigate the behavior of the material, such as pigments and binders, available in our laboratory as reference material when they are submitted to high temperature. In this way, we can study the phase transformation of the materials in controlled conditions and simulate thermal degradation. Among the published research, one of the most known examples is the blackening of azurite and its transformation into tenorite due to high temperatures caused by the proximity of the candles like reported in the study of mural painting of in St. Augustine Church in Siena, in Italy. The same situation was reported in the study of Byzantine mural painting in the Thessaloniki Cathedral, where the tenorite was found like secondary product due to the firing inside the church. In addition, a phenomenon of dehydration of goethite with the consequent formation of hematite was recognized as a consequence of high temperature. In the other hand, it's very important to know the sensitivity of the material in order to avoid their thermal degradation due to the high laser power during Raman analysis. Lead-based pigments, widely used in the ancient time, are known to be very sensitive where they are analyzed with Raman spectroscopy. Here is shown a research that underlines a misunderstanding due to a phenomenon of degradation caused by the high laser power during the Raman analysis. The Raman spectrum of massicot generated by the degradation of lead dioxide platinoite due to the laser irradiation as wrongly attributed to the secondary product of lead pigments. The interest in the study of the behavior of lead pigments comes from the investigation of a blackening phenomenon found on the surface of Gothic mural painting preserved inside the St. Stephen Chapel in Montani, in Italy. During a first screening of the blackened areas with X-ray fluorescence, we detected lead and lead Raman analysis carried out in the laboratory confirmed the presence of black platinarite present on the surface like a secondary product. Lead oxide have a very weak Raman spectrum, and you need to perform Raman analysis with a very low laser power. Thus, to the sensitivity of these materials also found during the Raman analysis of the wall painting samples, we have decided to perform a study of the phase transformation on sample of synthetic platinarite. At first, analysis in the same point showed that the spectrum of platinarite with its characteristic bands was visible up to 10% laser power. The temperature increase due to the effect of the laser between 10 and 50% was very high and did not allow the visualization of the spectrum of red lead, which generally is formed as a first degradation compounds. In fact, with the 60% laser power, the only well-defined band was that of the massicot, while the other band were barely visible and show a transformation into red lead and massicot. At maximum laser power, the spectrum of the massicot was visible, with the band shift towards shorter wavelengths, together with the band belonging to the red lead. After cooling, the Raman spectra obtain a low laser power show the band of litharge and red lead. In this case, the massicot formation did not take place completely despite the high temperature reached with the maximum laser power, because the massicot formation was reversible and this compound did not appear in the cooled sample. Analysis in a controlled condition was performed by cooling the Raman spectrometer to a Linkam temperature controlled stage, which allowed to vary in the sample temperature and keeping it constant during the analysis. In this way, commercial platinarite samples were heated by increasing the cell temperature to verify the temperature range at which the phase transformation of lead dioxide platinarite occur. The Raman spectra were collected starting from room temperature up to 600 degrees. For temperature above 300 degrees, a water circulation pump was used to cool the stage. In addition, some tests were carried out in order to choose the minimum laser power to collect a good characteristic Raman spectrum of platinumite without causing the thermal degradation. In this experiment, we verified that first phase transformation of platinumite takes place at a temperature between 365 and 370 degrees. In fact, in this interval, a broad band at 465 centimeters at -1 appears, together with the platinumite band, which become increasingly evident in the samples subjected to temperature higher than 375 degrees. X-ray diffraction analysis were carried out to identify the intermediate phase that had formed during the heating. And the analysis of the platinumite sample heated to 400 degrees allowed us to identify a mixture of the tetragonal platinumite and a complex monoclinic lead dioxide. On the other hand, analysis of the sample heated to 450 degrees showed that the dominant phase was the complex monoclinic lead dioxide compared to the tetragonal platinumite. In addition, thanks to the use of the temperature control stage, it was possible to attain a gradual degradation of platinumite, and all phases were shown. The figure shows the gradual transformation from red lead into litharge and then massicoat. Following the formation of red lead with the bands moving to a lower wavelength to do the heating of the sample, an increase in the intensity of the bands are visible as the increase of temperature. Although the phase transformation between red lead is evident at 500 degrees, the subsequent transformation occurs gradually. At 560 degrees, the transformation from red lead to litharge starts, and only the bands from red lead was visible, which lost intensity. In the spectrum collected at 570 degrees, only the bands of litharge were present. In addition, between 590 degrees and 595 degrees, the phase transformation between litharge and massicoat occurred, with the formation of the massicoat at maximum laser power, which remained even at 600 degrees. The same phase transformation was represented also in the 3D graph that show the phase transformation from red lead to massicoat. The phase transformation is evident even from a chromatic change from black platinumite to red massicoat. In this graph, the evolution of the Raman spectra of synthetic red lead is shown. Unlike commercial synthetic pigments, which have shown good stability at high temperature, the degradation product of platinumite show a broadening of bands and a shift toward lower wave numbers as increased temperature. This fact is very important from a diagnostic point of view because allows us to be able to recognize lead oxide when they are present as pigments voluntarily used by the artist, or if they are the result of the platinumite degradation. So, experiment carried out using a temperature controlled stage show the progressive degradation of red lead and then massicot. It allows to some aspects belonging to different phase transformation, which it had not been possible to obtain by the same point analysis by varying the laser power. However, the degradation process was reversible, since the only contribution of the laser beam, even if it is used at maximum laser power, was not enough to obtain a stable form of massicot. The research showed that it's very important to know the behavior of the materials at high temperature, and that attention must be paid to possible changes during Raman analysis. For these reasons, tests on the stability of the material should be carried out before Raman analysis on real samples, with the aim to avoid erroneous characterization of the materials. Thank you very much for your attention.
Thank you, Ilaria. That was excellent. Let me pass back to Manuel.
Okay, thank you, Ilaria. Now we are going to show you a second example. This is related with our research on possible sulfates we can detect in Mars and in extraterrestrial meteorites. We have conducted an extension of the initial research on calcium sulfate to mixed calcium-potassium sulfates. And we wish to understand the interrelationships of the different compounds here and its possible formation in Mars, either in environmental normal conditions, like in Earth, or in hydrothermal ones. Because 3,200 million years ago, the climate in Mars was like the climate here in Earth, with the absence, probably, of organic matter. And we have used it, again, Raman spectroscopy to follow the changes of the stoichiometries of the different compounds during the changes of temperature. I'm going to present you to Jennifer Vidrobro. She has been working in this project that the first paper has been 1 week ago published in astrobiology with these 3 compounds: gypsum, syngenite, and gorgonite. Gypsum is calcium sulfate only. Syngenite and gorgonite are 2 mixed calcium and potassium sulfates. And she's going to give you some details on this quite nice work. Jennifer?
Thank you, Juanma. I'm going to share my screen. Well, this is Jennifer Vidrobro, and I am my second year of the PhD about Earth and planetary science. With this presentation, we are going to show you how we use the temperature control states of Linkam in order to create a powerful database about Martian compounds that are sensitive to temperature changes. Well, let's start. One of the most important studies when exploring a planet is to know its mineralogy. This can be studied by orbiters, landers, which are static robots, or, for example, rovers, which are mobile vehicles. In this way, last summer 2020, NASA launched its rover Perseverance to Mars, and it's going to land this Thursday, February 18. The landing site is the Jezero Crater, and this is a fake illustration of the crater of a billion years ago, occupied by water and forming a lake. We know that this site was occupied by water thanks to the data we received by the orbiters that have detected hydrated minerals in this area. In order to study the mineralogy, the Perseverance rover is equipped with a Raman spectrometer inside the supercam instrument. In the same way, next summer 2022, the European Space Agency, together with Roscosmos, will launch the Rosalind Franklin rover to Mars, specifically to Oxyaplanum. Unlike the Perseverance rover, it will be equipped with a Raman spectrometer inside the analytical laboratory drawer. Well, as I said before, orbiters have already detected hydrated minerals on Mars. This is a global map of hydrous minerals already detected on Mars. The red dots correspond to the detections of the CRIMS instrument on board the Mars Reconnaissance Orbiter, whereas the blue dots correspond to the Omega detections on board the Mars Express Orbiter. Besides, I have circled in red the landing site. On the right, the Jezero Crater, and on the left, the Oxyaplanum. And you can see that the landing zones have hydrated minerals. Well, similarly, thanks to other orbiters such as Mars Odyssey, maps of the subsurface size can be created. Thanks to the gamma ray spectrometer, we know that the poles of Mars are rich in subsurface ice, whereas the landing zone have less concentration of subsurface ice. Well, you can see that the water plays a very important role in the mineralogy of Mars, but until today it has not been taken into account that the temperature on Mars can range from -140 to +30 Celsius degrees. This large temperature difference can affect minerals, especially those that have water molecules in their crystalline structure. In this way, our objective is to create a powerful database about mineral transformation due to temperature changes. With this presentation, we will be able to interpret quickly the Martian Raman spectra at the time of their arrival, to know at what temperature the minerals were formed, or to relate the detected minerals to other minerals within its chain of thermal transformation. Moreover, this database will be transferred to other fields, such as other planets, icy moons, meteorites, or other terrestrial fields. In this way, we could simulate the Martian temperatures thanks to the Linkam temperature control state, and we get the spectra, the Raman spectra, thanks to our micro-Raman spectrometer that we have in our lab. We simulate, as Juanma said, we simulate the conditions, the Martian conditions in three sulfates: gypsum, which is the hydrated calcium sulfate, syngenite, and gorgite. These last ones are the hydrated calcium and potassium sulfates. Well, we choose these minerals because gypsum have already detected on Mars, and syngenite and gorgite are potential sulfates from Mars. In this way, we synthesized these compounds in the lab, concluding that syngenite doesn't need hydrothermal conditions to be formed, whereas gorgite does need hydrothermal conditions to be formed. Well, the high temperature experiments were done from 40 to 400 Celsius degrees. Although the highest temperature on Mars is 30 degrees, we decided to reach 400 degrees because when meteorites enter into the Earth's atmosphere, they reach high temperatures. So we decided to choose this range of temperature. In order to keep the circuit cold and to avoid overheatings, we use the water circulation pump. The results of the gypsum are summarized here. When the temperature rises 200 Celsius degrees, the gypsum lost all its water molecules, transforming to anhydrite, which is the anhydrous calcium sulfate. In the case of the syngenite, when the temperature reaches 400 Celsius degrees, all the syngenite is decomposed into arcanite, which is the anhydrous potassium sulfate, and into lambinite, which is the anhydrous calcium and potassium sulfate. Finally, when the temperature is up to 180 Celsius degrees, part of the gorgojite is transformed into gypsum. In the case of the low temperature experiments, we decided we used the range of temperature from 0 to minus 100 Celsius degrees. In order to reach these temperatures that are below the room temperature, we use the liquid nitrogen pump and obviously the liquid nitrogen. In these results, in one case, we saw Raman sips of the main Raman bands, but we could see that the water bands undergo different changes. For example, in the case of the gypsum, at a temperature of 0 Celsius degrees, the first band of the water was lower than the second one. But when the temperature drops, the first Raman band of the water became higher than the second one. However, this observation wasn't seen in the case of the syngenite and gorgojite. In these cases, we only see that when the temperature drops, the main Raman band of the water became clearly and sharper. This is the case of syngenite and this is the case of gorgojite. So we can conclude that when the temperature increases, the main Raman bands of the primary compounds moved in their weight number, and the effect of the low temperature doesn't produce any change in the band's position, although the water bands are more clearly observed. So we could simulate the Martian temperature thanks to the control states, the temperature control states of Linkam, and thus create a mineralogical database based on temperature changes. And we hope that this database will be increased over time. This is all, and thank you very much for your attention.
Thank you, Jennifer. That was another excellent presentation. So let me share back my screen again. And so that's the end of our presentations, but we're very, very keen to hear some questions from anyone in attendance. You can ask any question you would like by typing it in the chat. You should see a link to the chat at the top of your Teams window, and that will allow you to type a question in if you wish. If you're unable to do that, you're very welcome to send by email, and we'll respond to them at a later date. So let me start with a question of my own. So let's see. So firstly, a question for Ilaria. So when you talked about your Raman analysis, you said that you have a very low signal when you're measuring the lead. So how do you deal with the background? Presumably, if you have a low signal, background is an issue. How do you account for that? And is there any concern when you change temperature that the background readings change? So, Ilaria, I think you'll have to unmute yourself, maybe you can answer that one. Or Juan Manuel, feel free to step in.
Okay, I can go with the answer. Looks like Ilaria has when we perform all of this work, we study the signal-to-noise ratio. And this is true that the background changes with the temperature, but not the real noise, but the associated fluorescence. So we need to perform some kind of pre-treatment to flattening the response and to avoid as much as possible the fluorescence. And then applying, if we have or not signal, with the criteria of selecting an adequate signal to noise value. So if we are sure that we are in front of a Raman band, we continue. If not, we perform another experiment, because maybe changing from one spot to other, the background decrease. And of course, this is a problem, especially when the Raman scattering of the compounds we are searching is really low or poor.
Okay, thank you, Manuel. I think that pretty much answers my question. I did have another question about this, just regarding the way you actually went about doing the experiment. So you showed, Hilaria, you showed how you held the temperature for a while and then you increased the temperature. I just wanted to clarify, at what point did you collect the Raman data, or did you collect the spectrum? Was I presume that that's during the hold time? Is that right?
Sorry, Robert, I have a little problem of connection, but I try to avoid the problem of the increase in temperature due to the laser power. I have performing different tests to obtain good Raman spectrum of laterite with the minimum laser power. And the minimum laser power used during all the analysis and during for the construction ramp was 0.5% of temperature. And I have verified that with this temperature, this laser power, I can obtain a good stability of the sample without provoke a degradation of the planetite due to the laser power.
Okay, that's a great, even better answer than my question. So that answers how you account for the increase in temperature from the Raman laser. So yeah, that's excellent. So if anyone else has any questions for Hilaria or Jennifer or Juan, please feel free to let us know. If I don't see any in the chat, so I'll continue with my own questions. Moving on to Jennifer. So again, really interesting, and thank you very much for sharing this. So you touched on something, and I don't think you really went deep into the explanation, but you said that for each of the materials, when you looked at the intensity of the Raman spectra, for some of them you saw that the intensity increased sort of perhaps as you would expect, but for the gypsum you saw that the intensity of the peaks switched. So I wonder if you could go into a little more detail about why that might be.
Well, at the moment, we don't know why the water bands suffer different changes. Actually, we have to research in this with this situation, but it could be that the water molecules change in their crystalline structure. Maybe they are the same, but they change the crystalline structure. But we have to work in this more. Yeah.
Okay, fair enough. Yeah, good to know. But yeah, quite interesting phenomena there. Let me ask another more general question, I think, to everyone. So, of course, a lot of the aim of this and a lot of stuff you've been doing is to prepare yourself for perhaps analysing some real samples from Mars as opposed to the simulated ones. Can you talk a little bit about what, if any, differences you might expect to see and how you will understand those differences or identify them? Because I know that being said that you've looked at a lot of simulated materials, I think. Perhaps that one goes to Manuel.
Okay. From a chemical point of view, the gypsum in Mars and the gypsum in Earth is more or less the same. The question is not in the mineral, the question is in the response of the Raman instrument. We have made our research work with high-resolution Raman spectrometers. And the Raman in Mars are with a different resolution. In the test we have made with SuperCam, gypsum is quite well detected. Also, the basanite. Basanite is the half-hydrated mineral phase of the calcium sulfate. And it's really critical to detect the water response more than the main sulfate vibration. We can detect also the main sulfate, but the most interesting area of the Raman spectrum is the one related with the water. And from the position of the weight numbers in the maximum of the water bands, we can also identify, if we have an adequate database, the chemical species, unless the Raman response of the SuperCam or ExoMars in the Raman laser instrument in the next mission from Europe is, of course, worse than the one we have with the high-resolution devices here in our lab. But we have detected another very important thing. It is true that the intensity or the area under the Raman bands is not the same, but the ratio of the band, yes. If you compare the SuperCam response with the INVIA response, it's nearly the same under the uncertainty level. This has been published by our group in the last Lunar Planetary Science Conference that was held last March virtually, because this was suspended the presential of the attendees. So we don't expect difference. The problem is if we can detect or not the mineral phases with the Ramans in Mars.
Okay, yeah, that makes a lot of sense, I guess. So it's in a way the work on the paintings and building materials using the less powerful Raman instruments may be the good preparation for this. So to ask about that, so I know you said some of these handheld devices are, I think it's a fantastic technique, but obviously that it has there are difficulties with portability, and the one that I was wondering about is the sort of physical stability. So I know that often you will use a really like a stable table or some kind of device to make sure you don't have any vibrations. And do you have anything like that out in the field, or do you just accept some background vibrations?
I'm going to give you an example on the work done in the field in a geoscience general context. We were during years performing some projects on the formation of beach rocks. Beach rocks are sedimentary rocks that can be formed in less than 30 years. This is incredible. And we have been monitoring how this evolves with the influence of the waves in the sea. And using portable instruments, we could detect some high hydrated mineral phases. Then we took the samples and removed it and sent to the lab. In less than 6 hours, the mineral phases changed to less hydrated. So since that expertise we gained some years ago, we used to perform as much as possible field measurements with our high-sensitive portable devices, even at the microscopic level, as I have shown you in some of the slides at the beginning of this webinar. Because we know that with humidity and with temperature, some hydrated species change it. And it is quite extremely important to be in the field to see if this is happening or not, because the important issue in the back of these changes is not the chemical meaning, it's the physical meaning of that. Imagine mirabilite. Mirabilite is the 10-hydrated sodium sulfate that can change to thenardite, that is the anhydrous sodium sulfate, if the temperature decreases below, let's say, 17, 16 degrees. At least here in our land near Bilbao, this can happen 3 or even 4 times per day. And we have detected that with the portable system. And the problem is the size. The molecule with 10 hydrated waters is 3 times higher in diameter than the anhydrous molecule. Imagine the physical stress from changing to 1 volume to 3 times the volume 4 times per day. There is little that can support that kind of physical stress without damaging. That's quite important for us to detect in the field the presence of the chemical species, especially the hydrated ones.
Okay, all right. Well, thank you for that very thorough answer, and that goes a long way to understanding some of the difficulties and the things that you need to be paying attention to here. So yeah, it doesn't look like there are any more questions. I think I'll just say again that if you do want to ask any questions, you're very welcome to send us an email or get in touch any way you can over our phone line, which you can find on the website. Please do get in touch. We're happy to hear from you. Later today or tomorrow, I'll send you a link you'll be able to view this back on demand. And also to anyone who wasn't able to join, we'll send that over to them. And in that, I'll give you a couple of links to some of the papers that we've talked about today from Manuel, Ilaria and Jennifer. So all just leaves me to say thank you so much to everyone for attending. I really hope you enjoyed this, and again, let us know what you thought. And thanks most of all to our presenters for some fantastic presentation, and thank you for your time. I'm sure this is a very busy period leading up to the landing of the Mars rover. I'm sure you're going to have a busy couple of weeks, and I hope we'll have a chance to catch up with you again once you've got your hands on some samples. So that's all from us. So thank you, everyone. Thank you presenters, and take care and stay safe, everyone. And catch up with you soon. Goodbye.
Thank you so much. Thank you.
Thank
Bye-bye.
you. Bye. Goodbye.
Bye. Thank you.